Hi everyone, welcome to
amazing channel of Brilliant Katha.
When you're rubbing one body with another body, electrons are transferred from one object to another object. Okay, this process, this type of electricity is being given a name.
halogen connected carbon sp3, then it's connected to benzene. See all of you, halogen connected. What is this carbon hybridization? Full single bond sp3, see then a benzene ring.
Denominator poles shouldn't be included in the denominator poles. That means the denominator, these -1 and -5 should never be included in the solution.
Homocircle caudal fin. It's giving two equal lobes. But in case of cartilage fishes, look at here, one big lobe is there, one small lobe is there. You cannot cut into two equal half this fin.
Brilliant Katha.
Good evening, everyone. Welcome to today's MCQ discussion session. Today we will discuss from 12th physics, electromagnetic induction and alternating current questions. Sorry for being a little late. We had some small technical issues, so I think it's perfectly fine now. I need some comments. Those who are online, just leave some comments and stay with me with the comments throughout the session. For the next 1 hour, we have to discuss some important questions from electromagnetic induction and AC, one by one, one after the other. As you know, electromagnetic induction and AC, these two chapters together is one particular unit. We have very important concepts in these two chapters repeatedly coming for boards, like both numerical questions and long answer questions, derivation questions, conceptual questions, everything. So these two chapters basically is like very important unit together, like for the boards. Okay, so in the chapter electromagnetic induction, see the major topics we know electromagnetic induction is a key concept, definitely. Yes, so we will be doing questions from all these particular units, because when you go through the past papers, especially for those papers we have MCQ questions like for the last few years, when you check, you can see questions are coming from electromagnetic induction from all the topics, especially when, as I always tell for beating MCQs, there is no shortcuts. What you have to do is like make all the concepts perfect in this chapter. So we start with like laws of electromagnetic induction. We have Faraday's laws and Lenz's rule, right? Faraday's law and Lenz's law. So we have questions based on both, right? Numerical questions, conceptual questions. We get questions from both the topics. We'll start with that particular concept, some questions, okay? Followed by that, we have self-induction. Before that, we have motional EMF. Yes, motional EMF. Motional EMF, then rotational EMF. We have rotating rods, we have rotating disc, right? That kind of concepts we learn from the chapter. Yes, then followed by self-induction and mutual induction. Both of them, we have numerical questions from that part 2, and generator. AC generator is the last topic from electromagnetic induction. Yes, so these concepts, like doing 500 or 600 questions from one single chapter or one single topic is not the way to beat MCQs. We know we have to make those concepts perfect so that we can beat any question, or like we can do any question coming from that particular topic. If you're okay with a particular topic and the equation, if you have any mathematical equation related to that, just make perfect your concept, and also remember the equation. That is enough to solve any MCQ questions that we get from these chapters, like from any chapters, from any concepts. Okay, so as I told you, we'll start with some basic constants from the laws of electromagnetic induction, Faraday's law and Lenz's rule. Okay, we'll start with that. Let's go to the first question. So the question number 1 is, you're given flux as a function of time in the question. Look at that. Flux in Weber in a closed circuit of resistance 20 ohm. All right. Varies with respect to time. Yes. Like time is given in second SI units. Okay. According to the equation, phi is equal to 6t square minus 5t plus 1. Okay. Right. The magnitude of induced EMF at t is equal to 0.25 seconds is, remember, not induced EMF, I read it wrong, induced current you are asked to calculate. So be very careful whether you are asked to find induced current or induced EMF. Read the question thoroughly and then start solving it. Okay. See, we know this is from the law of electromagnetic induction. We know how to find from the basic concept of electromagnetic induction. We know induced EMF is always rate of change of magnetic flux with respect to time. So will there be an induced EMF in this case? Yes, because flux varies with respect to time. Whenever there is a change in flux with respect to time, there will be an EMF induced for sure. Right. And it is a closed loop. We know inducing EMF is not the only condition to get some induced current. We know in the case of like open loops, if the loop is open, we will have induced EMF, but there is no induced current, right? Yes. If the loop is closed, only induced EMF produces induced current. So that also specifically given in the question. It is a closed circuit. Right. So if it is a closed circuit, we expect some induced current in it. So let us now calculate what will be the current. We know current in the circuit is going to be always induced EMF divided by resistance of the loop. Okay. So induced EMF E is going to be d phi by dt, rate of change of magnetic flux with respect to time, divided by the resistance R. So first of all, let us calculate what is that change in flux. See, phi is given as 6t square minus 5t plus 1. So on differentiating that, we get d phi by dt. I can say it is 12t minus 5, right? We know how to differentiate that function. Yes, so this is the induced EMF we have. Now, what will be the induced EMF at a time, at an instant of time? That is what given. So at the instant, what is the instant given? Time t is equal to 0.25. Yes. So t is given as 0.25, which is nothing but 1 by 4. We know, right? 0.25 is 1 by 4. So we can say 12 into 1 by 4 minus 5. So what are we getting? We have to consider minus d phi by dt, right? Yes. So this will be altogether minus, and we have minus of 12 by 4 minus 5, which is going to be 3 minus 5. We get minus of 3 minus 5, that is going to be plus 2, right? Yes. So 2 volt is the induced EMF. Remember, if you have a 2 in somewhere here, don't rush into the answer, straight into the answer. No, look at this. You are not asked to calculate induced EMF, induced current. Okay. So induced current I is now easily we can calculate because you are given resistance, which is E by R. Induced EMF is 2 divided by what is the resistance of the circuit? It is 20 ohm. So we get 0.1 ampere current. Yes. 0.1 ampere current is the answer for this particular question. So points you have to remember. See, when we get questions from induced EMF, induced current questions, you have to, as I told you first, you have to read the question properly. Whether you have asked to calculate EMF or current. See, if you solve this and we get 2, if you have one of the option as 2 here, without checking even the options, like the units also, we may select that option as our correct answer. So don't be in a hurry, read it properly. It is not EMF. First point. Second one, we'll do all these things. Later only we identify the circuit is not closed. Remember, if circuit is not closed, what will be the current in that circuit? 0. If you have a 0 in that option, you can go for that answer straight. You can save your time. Okay, so understanding the question properly is the first step, as always, of course. So then answer to the question. Fine. So that was the first one. Now, moving on to the question number 2. See, again, question based on electromagnetic induction, laws of electromagnetic induction. To be specific, question from Lenz's rule, right? Yes. So we have a current carrying conductor here. As per the question, current from A to B. There is a current flowing through the circuit from A to B. Yeah, you have given the direction. I hope it is visible. Right. So A to B is the current flowing through it. Look at that current. That current is decreasing. Current is decreasing. Right. It's a varying current. Right. We know for a straight conductor, we know the direction of magnetic field produced by the conductor. Below this wire, it will be a cross. We know when you apply right hand thumb rule, below the wire, it is a cross, and above the wire, it is a dot. Right. That is how we found it. Good. Now, we know magnetic field linked with this particular, magnetic field produced by a straight conductor is equal to mu naught I by 2 pi r, right? That is the equation. Magnetism, like application of Biott's Ampere circuit law, magnetic field due to a straight conductor. Yes. So what happens when this I increases or decreases? As per the question, it is decreasing. So if it is decreasing, magnetic field is also decreasing, which means you got a dot here which is actually decreasing. So it is a decreasing dot. We know as per the Lenz's rule, whenever you get decreasing dot, a decreasing field, it should be supported. If it is an increasing field, it should be opposed, right? So this is a decreasing field, and that decreasing field should be supported by producing the same magnetic field. So there will be an induced EMF in this coil because of the varying magnetic field, because of the varying current, of course, yes. And that magnetic field will induce a current in this coil because that coil is closed. Closed loop. Yes, that is a closed loop. And then what will be the direction of current? If you want to get a dot out of the screen, we know according to the right hand thumb rule for circular loops, the current should be counterclockwise, right? Anti-clockwise. So that should be the direction of current in this circuit. We have done many questions in this way, like in our revision classes and all. So I hope this concept is easy for you. Don't waste this much time for this question, right? Just apply the right hand rule, right? Find out whether it is increasing field or decreasing field. Just apply Lenz's rule there, find out the direction of current. These are all time saving questions actually, right? We need more time in section A because that is the terror session still for many of us, right? Right. Okay, fine. So second question, option B is the right answer. Now, moving on to the third one. Right. Look at the question. Question says, change in current of 0.01 ampere in one coil produces a change in magnetic flux of 2 into 10 raised to minus 2 Weber. In the other, okay, so there are two coils. Yes, we know when we keep two nearby coils, the concept already is loaded in our mind, right? So that is going to be mutual induction. Yes. So then mutual inductance in Henry for two coils. That's what we have to calculate. Mutual induction you have to find out for two coils. So look at the values given. There is a change in current, right? There is a change in current, 0.01 ampere. So we can say the change in current DI is 0.01 ampere. That is one of the given value. Next given value is quantity is magnetic flux. Magnetic flux is changes from like 2 into 10 raised to minus 2 Weber. That is what the change in flux produced. You are asked to find what? You are asked to find mutual inductance of the coil. Yes, mutual inductance M. Easily we can remember this equation, by the time that equation should load into our mind, of course. Right, magnetic induction, mutual induction is to be calculated. You are given current and you are given flux. Flux, induction, mutual induction and current, how are they related? Phi is equal to, yes, phi is equal to M into I, right? That is the equation, mutual induction. If it is one single coil, self-induction, because of its own varying current, there will be a self-induction. That also related in the same way, we know phi is equal to L into I. Yes. See what happens if I differentiate this. Change in phi, why there is a change in phi? Will there be a change in mutual induction? No, for a given pair of coil, for a given orientation, for a given circumstances, mutual induction is going to be a constant. Why there is a change in flux? Because there is a change in phi, current DI. You are given d phi and di, you're asked to find what is the mutual induction is. Done. So if you take just the ratio of d phi and di, you will get the final answer. So what is that? M is equal to d phi by di. So we can say d phi is what? 2 into 10 raised to minus 2 Weber divided by what is di? Di is 0.01. See, actually this is 0.02. right? This is 0.01. 0.02 divided by 0.01 is going to be just 2 divided by 1, that is going to be 2. So 2 Henry is the mutual induction of this particular coil, so that is your option C. Okay, so self-induction or mutual induction, we will come to more into this particular concept in some following questions. So whenever you are asked to calculate mutual induction, like this is one of the equation that helps you. Yes, we have like a different type of question we get from this part. We'll come to that soon. Okay, now next question. Yes, again a question to calculate induced current in the loop. Yes, look at that. A square loop of wire, side length of 10 centimeter is placed at an angle of 45 degree. Remember that loop is kept in a particular way in the magnetic field. Yes, it makes an angle at 45 degree with the magnetic field that changes uniformly from 0.1 Tesla to 0. Yes, magnetic field is decreasing from some particular value to 0 in a given time of 0.7 seconds. So you're given one angle theta here, which is 45 degree, right? And you're given some change in magnetic field. What is change in magnetic field? dB. It changes from 0.1 to 0. So that is 0 minus 0.1 Tesla. That is a change in magnetic field produced. In what time that change is produced? In a given time, 0.7 seconds. Right. These many informations are given. One more information. It is a closed loop, right? It's a closed loop and it has a resistance of 1 ohm. Resistance of the loop is also given 1 ohm. Right. Just work on that given quantities. Like, you know, we have to find out what is the induced current in the loop. Yes, induced current, okay? Not EMF. Yes. So induced current, if we want to calculate, as we just discussed before, I is going to be E divided by R. EMF we have to calculate divided by resistance of the coil, easy. So how will you find out EMF? Induced EMF always be calculated, you know, minus d phi by dt. Good. Law of electromagnetic induction, right? Faraday's law and Lenz's law together. Yes, minus d phi by dt. Now, what is that flex here? How much flex that coil linked, like, you know, that possesses? Phi. Phi can be calculated as BA cos theta, right? This is one equation we have to calculate, like magnetic flex. See, magnetic flex was related to mutual induction, right? You know, just before we used that equation. So phi is equal to BA cos theta, and you're given theta here. How much was theta? Area vector makes an angle 45 degree with the magnetic field. Directly you're given theta value is 45 degree because the theta in this equation stands for angle between magnetic field and area vector, we know. Yes, so theta is equal to 45 degree. We know cos 45 is going to be 1 by root 2. Right. So then, if you substitute this value here, what will be the EMF? EMF is going to be minus d by dt of what? B into A into cos theta is going to be what? 1 by root 2 cos 45, right? Yes. So in which, look at this equation, when the square loop is kept in a particular field, is its area varying? No, area is a constant. What is varying here? Magnetic field actually. So we can take that area value and 1 by root 2 out. So area into 1 by root 2 is going to be equal to, into what? dB by dt. We already know what is dB by dt minus of. What is dB by dt? dB is given, dt is given. That we will substitute here. Done. And we are coming to the point, like, you know, to the final answer soon. A, what is the area? Area of the square loop of side length 10 centimeter. 10 centimeter is the length side of the square. So 10 square, like, you know, 100 centimeter square is the area. So now just substitute the values here. So we get EMF is going to be equal to minus 10 raised to 2 minus 2, right? Like centimeters, I hope I can write it directly, 10 raised to minus 2, because 10 into 10 raised to minus 2, the whole square will be the converted form of centimeter to meter square, right? Yes, 10 raised to minus 2. And what else we have? 1 by root 2. Yes, 1 by root 2. And what is dB by dt? We have dB and dt here. dB is going to be 0 minus 0.1. So we get minus 0.1 divided by what? 0.7. Right, 0.7. So this is what EMF is. See, look at that. Don't be scared into that by looking into that calculation. It's easy because 1 by root 2 1 by root 2 is nothing but 0.707. So that's 0.707 and 0.7 can be approximated to, they can be cancelled, right? Yes, so that is gone because 1 by root 2 we know it is 0.707 exactly, right? So we have 10 raised to minus 2, minus and minus gets cancelled, into 0.1 we get 10 raised to minus 3, sorry, 10 raised to minus 3 volt. This is the EMF induced. Now we can go straight to the current. Current is the final answer. I is equal to E by R. Yes. What is your EMF? 10 raised to minus 3. What is your resistance? 1 only. So nothing more to calculate. Current is going to be 10 raised to minus 3 ampere, which is actually 1 milliampere, and that is our option A. Right? So that was a detailed discussion. We will not take this much time, of course, to solve this question. So here, the change was something different. Magnetic field was varying. That is why I explained each and every concept related to it. See, I hope, as I told you before, it is not about solving this question specifically. We are trying to understand how these kind of questions can be solved and what are the concepts related. Fine, that is the answer for the question. I hope it is clear. Moving on to the next one. The electric current in a circuit varies from plus 2A to minus 2A in a time 10 raised to minus 2 seconds. Right. Another coil of resistance 20 ohm. Yes, another coil. I kept 2 coils nearby. So the question is going to be related to mutual induction. Let's see. 20 ohm and inductance of 2 Henry. So which inductance is that? Is it self-inductance or mutual inductance? It's going to be mutual inductance because we kept 2 coils nearby, we know. So 20 ohm is the resistance of that nearby coil and 2 Henry is the mutual induction. Like it is placed near it, okay? It is placed near it. What will be the induced current in the second coil? Yes, so we have to find out what is the EMF induced in the second coil. You are given change in current. And we know EMF induced, change in current, and you are given like in a time, current is changing in a time. So basically you are given some values. We have DI, we have DT, and mutual induction is given. You're asked to find what is your induced EMF. See, a question straight from mutual induction. We have the relation EMF induced is going to be equal to minus M di by dt. In mutual induction, this is the EMF induced in a neighboring coil. Right? The same equation, just like phi is equal to Mi, is equivalent to phi is equal to Li in self-induction. Correct? In the same way, EMF induced in one single coil is E is equal to minus L di by dt, because we differentiated phi is equal to Li. So L di by dt, L is a constant. The same equation we have, phi is equal to Mi. That is how we got it, right? Yes. So M di by dt. Right? So we have all the values except E that is to be calculated, and we get minus mutual induction is given 2 Henry into DI. What is change in current? Final current minus initial current. Final minus initial current. Yes. So we have minus 2 of course, right? Yes. Divided by, what is the time taken for this? 10 raised to minus 2. Correct? Done. So then what is the value we get finally? So minus 2, and this will be minus 4. It becomes plus 8 divided by 10 raised to minus 2. So we get 800 volt. That is the induced EMF. And you are asked to calculate induced current with the resistance given. So as just like in the previous question, I is equal to induced EMF divided by resistance, and that is 800 divided by 20 ohm. So that is going to be 40 ampere. That is the current induced. Right? So 40 ampere is the last option. Okay, so mutual induction part, like phi is equal to Li, phi is equal to Mi, and its differentiated form, differentiated form like d phi by dt for both M and L. So we used all those equations in these few questions. Right, okay. Now, look at this question coming from, whenever we see this diagram, the first concept that should come to your mind is something moving, right? Motional EMF, a movable arm. A movable arm is moving in a magnetic field perpendicular to the screen. Yes, so what should you remember? What is the EMF induced in it? Yes. So how will you calculate EMF induced in a motional EMF? Right? It is B LV. We know the equation. Magnetic field strength, length of the conductor, V is the velocity with which we move the conductor. Let us go to the question now. Let's see how is it related to. Figure shows a conducting rod PQ. I hope you can see the conducting rod. I can just mark it here. This is the PQ they are talking about. Okay, the straight conductor. In contact with a metal rail RP and SQ. See, RP is this side. See, this is RP and this is SQ. RP and SQ. Yes. Then, which are 25. Yes. Okay, fine. So, sorry for that. See here, as I told you, we have to read the question properly. Many informations are given in the question. We solved it. Like, we infer from the question, the diagram itself, and then we solved. Remember to find the direction also. Right. Good. Moving on to the next question. Okay. Motional EMF, right? When a conductor is moving through an external magnetic field, that is what we did in this previous question. And the condition we know, magnetic field length and velocity should be mutually perpendicular, and that condition was satisfied. Now, look at this. A special case of that motional EMF, which is rotating rods, right? That is what we explained. And we didn't have that derivation. We have a final equation for that. EMF induced in a rotating rod is equal to half B omega L square, where omega is the angular velocity of rotation, L is the length of the conductor, B is the external magnetic field. So let us check what are the informations given, and we can solve it straight. A metal conductor of length 1 meter, yes. Alert, yes, we have given the length there, fine. Rotates vertically about one of its end at angular velocity 2.5. Yes, angular velocity we know we denote it by omega. It is 2.5 by pi rotation per second. That is what RPS we know. RPM and RPS, rotation per second and rotation per minute. So here it is rotation per second given, right? Length of the conductor was given, which is 1 meter, yes. Now, external magnetic field. Here, the external magnetic field is the magnetic field produced by the Earth. Earth horizontal magnetic field is given. So the conductor is vertically rotating, it's rotating vertically like this. This is the way how it is rotating. And horizontal magnetic field is going like this. So magnetic field, length of the conductor, so that is how the setup is arranged. Now, magnetic field strength is given 0.2 into 10 raised to minus 4 Tesla. Good. All values are there. Right? We have just substitute and simplify with one specific point you have to remember. RPS is not SI unit. Right? We cannot use RPS. It should be, if it is omega, omega should be radians per second. So how will you convert RPS into radians per second? We have to multiply with 2 pi, right? Multiplying with 2 pi. Then it will be converted automatically into radians per second. So that conversion is the key concept in this chapter. Most of the time, if you do without conversion, a matching option will be there in out of these 4 options, and we will end up with that result, which is basically wrong. Okay, so be careful. Radians per second is not SI unit. Radian per minute is also not SI unit. It should be converted to radians per second. I mean rotation per meter. Right? RPS is going to be rotation per second. RPM is rotation per minute. Good. Then we can cancel this pi, and what is this value? 5 radians per second. See, the values are given accordingly, right, to make it simpler. So now let us move on. What is the expression for induced EMF in a rotating rod? What did I tell you? E is equal to half B omega L square. Half B omega L square. We have all the values. Half into magnetic field is 0.2 into 10 raised to minus 4 into omega is now converted form of omega is 5 into L square doesn't make any difference because it is just 1 square. Correct? Yes. So then we can cancel this 0.2 and 2 as 0.1 here, and we get 5 into 10 raised to minus 5 altogether. Yes. EMF induced is going to be 5 into 10 raised to minus 5 volt. Unfortunately, we don't have a volt option. Instead, it is given in millivolt and microvolts. So in these kind of questions, be very careful, when it is given in some different units, in the sense, some smaller units, that conversion, if you commit a small mistake, there will be other matching options. Even your, you can find an option which, you got actually may be wrong. So be very careful in the conversion. So we have 5 into 10 raised to minus 5. So millivolt, it is not 5 millivolt. 5 millivolt means 5 into 10 raised to minus 5. So this is not 50, also not fine. If you are going to make it 50, it will be 10 raised to minus 6, right? So we have only 5 and 50 values. Magnitude is 5 or 50. So if 5 is not matching, now if you just make it 50, 50 into 10 raised to minus 6 volt is the another form of the same value. 10 raised to minus 6 volt is nothing but microvolt. So option B is the matching one. Okay. So this is what we have to do. A question from a special case of motional EMF, that is rotating rod. A rod was rotating in the external magnetic field. Half B omega L square. Done. Moving on to the next. A circular coil of radius 8 centimeters and 40 turns is rotated about its vertical diameter with an angular speed of 25 pi radians per second. Yes, nothing to worry about the values, it's radians per second. Good. In a uniform horizontal magnetic field of magnitude 3 into 10 raised to minus 2 Tesla, the maximum EMF induced in the coil. Remember the difference. Before, it was just a conductor rotating, right? In a rotating rod. We have specific case of rotating rod in an external magnetic field. That is how we used the equation half B omega L square there. What actually happens in this particular case? Here, we can say it's a like circular coil. It has a radius 8 centimeters and it is rotating about a vertical axis. See? Rotating about a vertical axis. So whenever a loop is rotating in an external magnetic field, what comes to your mind? When I say this, it's going to be AC generator, right? In AC generator, between the pole pieces of a bar magnet, one armature coil is rotating, right? Mechanical energy is converted to electric energy there. Yes, so there is a rotating loop, and we know shape of that loop is irrelevant there, right? We just need the area of the loop, whether it is a square loop or circular loop or irregular shaped loop, it doesn't matter. Here we get a circular loop which rotates in an angular, external magnetic field. So it is nothing but an armature coil in the generator. Yes. So what was the flux linked with this coil? Flux linked with this coil phi is equal to BA cos theta. That is what we know, BA cos theta. And there are n number of turns, so it will be n BA cos theta, right? And this theta, we replaced that theta as omega t, and we got phi is equal to n BA cos omega t. This was the flux linked with that particular coil. How did we calculate EMF induced? EMF induced d phi by dt, right? Minus d phi by dt, that was the induced EMF in this case, and that is going to be NBA omega sine omega t. So we have a minus sign here, differential of course will be minus, so that will be cancelled. We know that particular part. I am just looking to this particular equation in which NBA omega was called E naught, right? Maximum EMF induced, because when the armature coil rotates, instantaneous voltage induced in it will be different for different instant. That is why it is called instantaneous voltage anyway. So this is the maximum value of voltage induced. And interestingly, in this question, you are asked to calculate only what is the maximum EMF induced in that particular coil. So when a coil is rotated, how much maximum EMF induced in that? So we have to just calculate what is NBA omega. Done. If you know this equation, straight you can substitute. I was just explaining the backdrop of the story, So N is what? 40. 40 turns into magnetic field B is given. What is the magnetic field? 3 into 10 raised to minus 2. Yes, 3 into 10 raised to minus 2 is given. And it is a circular coil of radius 8 centimeter. So pi into r square. 64 into 10 raised to minus 4 is what? That is 8 centimeters square in meters, right? And that is area into, what is omega given? 25 by pi. Cross check once again. Should we convert this? No, because it is given in radians per second. Done. Cancel these values, pi gets cancelled. And we have 40 into 25 is going to be 1000. 1000 into 3 into 64 into 10 raised to minus 6. So we get 3 into 64. So it is simple. 3 into 64 into 10 raised to minus 3, and that is going to be 192 into 10 raised to minus 3. 0.192 is the correct answer. 0.192 is one of our options, that is option C. That's the correct answer. Okay, so whenever something is rotated, make sure what you're answering the question, right? Properly by using specific or that particular equation to the question, then only we will get the exact answer. Understand the question, don't be in a hurry. We know we have some 16 questions to finish in section A. So we always be worried about what are these kind of questions, of course. So don't commit mistakes there. Understand the question properly. It will be simple. Don't make it complicated by reading wrong. Okay. So make sure you're reading it properly. Then start choosing equation wisely and then simplify it. Moving on to the next. See, a circular coil has a 500 turns of wire and its radius is 5 centimeter. The self-inductance of the coil is, self-inductance of the coil phi is equal to, we know for a specific solenoid, if you have a solenoid, L value we know mu naught N and A or something. So we have specific equation for that. So here you are given some random circular coil. You're asked to find how much is the self-inductance of that particular coil. Remember, whenever you're asked to calculate self-inductance or mutual induction, inductance of a particular given arrangement, a pair of coil or a single coil, you remember how did we derive it for solenoid? We calculate flex in two different ways. First, we know the actual equation for flex for any particular loop. Flex linked with that is going to be BA cos theta. We will find out flex using this equation. If you have n number of turns, that also should be counted. It should be NBA cos theta. Correct? Then that is one way of doing it. And in the same way, we can find out flex in terms of self-inductance, which is equal to L into I. So these two equations we equate and simplify. That is how we find what is the value of I. So when you equate them, see, if I equate Li is equal to NBA cos theta, we can cancel, we can find out what is L. And the problem with this solution, we don't have any current given. So if you want to substitute the value of current I, we don't have that value in our question. So what happens? We have to assume some current, So this is the current carrying loop. Imagine we have magnetic field at the center, which is a dot. It is going out, and current is anti-clockwise, area of the loop is also going out, so that magnetic field and area vector has an angle 0 degree. Cos theta is equal to 1, right? Cos theta will be 1. So in this equation, what happens to the cos theta? It reduces to 1. And what will be magnetic field at the center of this loop? What is the magnetic field here? We know for the center of a loop, circular loop of wire, magnetic field is going to be mu naught I by 2R, where R is the radius, or 2A. A should be the radius. Okay, so now we can substitute that value of B here, and cos theta reduces to 1. We'll end up with the result. See, Li is going to be equal to N into mu naught I. Wait, we have to be careful. See how many loops of wire are there? You're given 500 turns. So if you have 500 turns of wire, you have to multiply this with the number of turns also, right? Not only for the flex. The current magnetic field produced by a circular loop is also proportional to the number of turns. So each number of turns produces mu naught I by 2R. So if you have n number of turns, multiply with n. Done. So n into mu naught I, there is one more n also, because that is coming from this, mu naught I n by 2R into what? Pi r square. Correct? Cos theta is gone. Cos theta is 1. Now simplify this, and interestingly, see, look at this, I is gone. We are not given any current there, and that current is not needed in this calculation. So now it is easy. L is equal to, substitute those values. Number of turns is given as 500 into 4 pi into 10 raised to minus 7 into 500 once again. Yes. Number of turns. See, one of the R gets cancelled from this. So the whole divided by 2 into pi into, what is the radius given? Radius of the circular coil is 5 centimeters. So we can say into 5 into 10 raised to minus 2. Okay, now we can just simplify this and make sure you are just taking it properly. So when you simplify this, there will be a pi square in this term. So we can just, I'll just proceed here. 4 pi, right? So these 2 and this can be cancelled. So 200 and this is going to be 1000. 1000 and see 1000 into this 500 into 5 is going to be 2500. I'm just simplifying it further. 10 raised to minus 9. 10 raised to minus 9, and we have a pi square here, and I hope you remember I told you before, pi into pi is pi square is approximated to 10. You will get an approximate value there. See, it can be 10. Pi square is 10. 9.85 something. Usually in our calculation we can approximate that into 10. So that will be easy now. So divided by what? Nothing, because that 2 is gone, and the thing is the denominator. When you simplify this, you will get 25 into 10 raised to minus 3. See, all other 10s will be simplified. Powers of 10, 10 raised to minus 3, which is 25 millihenry. Okay, taking pi square as 10 approximated. Okay, so this is how we found the self-inductance, and we know this technique we use it to derive self-inductance of a solenoid. Even in small numerical questions also we can do the same. Equating two equations, one in terms of self-inductance or even mutual inductance, if it is mutual induction question, then other equation is BA cos theta, right? And take your B wisely, substitute and simplify. Moving on to the next. Here again, a similar question. You can see two coils given, so definitely it will be some mutual induction. Let us see. O is a center of two coplanar concentric circular conductors A and B of radii R and R capital R respectively, as shown in the figure. Here R is very much less than capital R. The inner radius, the inner circle is very small compared to the outer one. The mutual inductance of the system can be, what is a mutual inductance of the system? Here also we can do the same thing, right? So the external, this outer coil, which carry a current I, produce a magnetic field in this region, which is enclosed, which produce some flux in the inner coil. So what can be that magnetic field B? Which is mu naught I divided by 2 into radius of the outer coil. That is a magnetic field, right? So we can say, before it was self-inductance, L into, right, no, phi is equal to L into I. Here it is mutual induction, so we take the other equation, phi is equal to M into I, which can be equated to BA cos theta, right? So we are going to calculate flux linked with this particular coil, the inner coil, which is kept in the magnetic field of the outer coil. Yes, so we can say M into I, right? M into I is equal to B. B is produced by the outer coil, which is mu naught I divided by 2 capital R into area of which coil? Area of the coil whose magnetic flux is to be calculated, right? So that is the inner coil, which will be pi into small r square, inner coil, right? Into, what is cos theta here? Cos theta is the angle, theta is the angle between direction of area vector of the inner coil and magnetic field produced by the outer coil. See, we know anti-clockwise current, magnetic field will be out of the screen, area vector is always perpendicular to the screen, like to the plane, and they are in the same direction. Cos theta becomes 1, theta is equal to 0. Yes, so now we can just simplify this. I gets cancelled from either side, just like in the previous question. I gets cancelled. Mutual induction we got directly mu naught I pi R square divided by 2R. Sorry, I is gone, right? No more I. Sorry. Mu naught, what else? Mu naught pi R square divided by 2R. Yes, mu naught pi R square by 2R is our option A. That is your correct answer. See, so whenever you're asked to calculate mutual induction or self-inductance of a given coil, we did the same method. We equated two equations. One, phi is equal to M into I if it is mutual, phi is equal to L into I if it is self. Equated to BA cos theta and be simplified. Done. Coefficient of mutual induction of primary and secondary coil of an induction coil is 5 Henry. Yes, mutual induction is given, which is 5 Henry. Current of 10 ampere is cut off in 5 into 10 raised to minus 4 seconds. The EMF induced in volt in the secondary coil. So now this question is going to be very easy. We know already. We have done some similar, not exactly the similar question. We have the equation. See, what do you mean by that current is cut off? There is a change in current. Current is cut off means when the current is cut off in the circuit, no current flows through it. So there is a change in current produced, dI 0 minus 10 ampere, right? Final current is 0 because it is cut off, and initial current was 10 ampere, so 0 minus 10. What is time taken for that? dt is given 5 into 10 raised to minus 4. You are given mutual induction, M is equal to 5 Henry. We know the equation, just a straight question, EMF E is equal to minus M di by dt. So M is 5 Henry, Di is minus 10, see minus already here, divided by 5 into 10 raised to minus 4. Correct? That was the time taken. See, what can you see? Minus and minus gets cancelled, 5 and 5 gets cancelled. See, this is gone. So 10 raised to minus, that 4 comes up. The 10 raised to minus 4 becomes 10 raised to plus 4. It becomes 10 into 10 raised to 4, which is 10 raised to 5 volt, which is option B. This was a direct, easy question, so I won't spend much time on that. AC generator. We are coming to the AC generator part, the last part of electromagnetic induction. With N turns, same area, the maximum value of EMF generated. It's a direct question. If you know the equation, you don't have to waste time on this. What is the expression for maximum EMF produced? Just before we use it in a question, which is NBA omega, right? So equations we usually learn in a particular order. I remember NBA omega. So when the omega is shifted to the other side, I'll be confused. Right? So that is how we confuse it with the equation. So whether it is omega NAB or NAB omega or it is N omega AB, whatever may be the order, choose the equation carefully because it seems like identical, all of them. Right. Fine, that are some questions from electromagnetic induction. See, it was quick. Yes, some basic concepts only we touched. Some different kinds of questions. I tried to add maximum like 2 or 3 questions were from past papers also, from the questions that we discussed. So this is the way how we get questions from electromagnetic induction. Numerical questions, conceptual questions. See, Lenz's rule, we get directly nothing to calculate there, just concepts we added, and direction of induced current, that kind of questions, including numerical questions. Both are coming from the chapter. Now, when we move on to the AEC, see, alternating current, we have the basic concepts we know, the basics of AC. Like what is RMS value, what is mean value, what is average, maximum peak value, like what happens in one complete cycle, like, if you take the average, that kind of basic concepts that makes, the basics of alternating current equation part, like, concepts part, followed by, we explained AC circuits in the sense AC passing through resistor, capacitor, inductor separately. Those concepts should be perfectly fine, then only you can enter to LCR circuit with confidence, otherwise you can't go. So make sure these 3 concepts are perfectly fine conceptually and like mathematically. Not only for MCQs, we have long answer questions also from that part, So then after this, we combine them together to form LCR circuits. Yes. So LCR circuit, they are all just listed under this particular column, and resonance of LCR circuit. Right? Yes. So how impedance and reactance are related? Like what are the differences basically? Like, that kind of questions, that kind of concepts you have to make sure. And then finally, we have transformers. As a last part of the AC, we have a small topic, transformers. We get repeating numerical questions from that part, okay? So make sure you are just revising them properly. We'll quickly go through some questions. We don't have much time. So question number 1 is from the basic concept of AC, of course. So we have current in ampere varies with time as I is equal to 3 sin omega t plus 4 cos omega t. Yes, RMS value of the current is, we are trapped because we learned I is equal to what? I0 sin omega t, right? V is equal to V0 sin omega t or cos omega t. So we know only up to that. So don't cheat us. This is not the way how we write it. But they have given, unfortunately, a combination of sine and cosine function that is a given current. Okay, see, we know when we get the questions like this, current amplitude is not one single value. We have 2 values of amplitude, 3 and 4. RMS value is always peak value by root 2. So if you're asked to select the peak value, we'll be confused. Like we have 2 values, right? Whatever comes here is our peak value. But unfortunately, we have one more term given. Yes. See, we know what is the resultant of like 2 like functions like A cos omega t, for example. A cos omega t plus B sin omega t. Or A sin omega t plus B cos omega t, whatever it may be. So the resultant amplitude of this function is going to be root of A square plus B square. That is how we calculate resultant amplitude, right? Resultant amplitude. Amplitude is nothing but the peak value. So peak value of this is going to be root of a square plus b square. Actually, it is a square plus b square plus 2ab cos theta, 2 resultant of 2 vectors, right? But why that 2 cos theta part is missing here? Phase difference between cos theta and sin theta is pi by 2, cos 90 is 0. Okay, that are all the concepts related to that, but whenever you're given the values like this is the amplitude, resultant amplitude. Okay, now it is easy. We know what is the resultant amplitude. What is I naught? What is actually our I naught? One single value we need, say, so root of 3 square plus 4 square, 3 square plus 4 square, which is actually 5. See, such a big or confusing question we solved is very simply. So if you know the concept, this is what happens usually in numerical questions, like MCQ questions. I naught is 5 ampere. Therefore, what is IRMS? IRMS is always maximum by root 2. So option C is the correct answer. Done. Moving on to the next. You're given in an AC circuit, current is 100 sine 200 pi t. The time required for the current to achieve its peak value will be. See, time taken to achieve the peak value. Peak value means the amplitude, the maximum value, highest value, right? In its like varying values, the peak value is the highest point in the graph. Look at the function, it is a sine function. See, we know how AC can be represented. If it is a sine function, varying as a sine function, this is how the one complete cycle can be represented, right? See, starting from t is equal to 0, if you have taken t along x-axis, yes. Back to this. See, as I told you, this is one complete cycle. Time taken to complete one cycle is what? Capital T, time period. What is this? Half of the time interval, right? T is equal to half of the time interval. Even half of that is going to be T is equal to 1/4 of the total time interval. So, what will be the time taken to attain peak value, maximum value for the first time? For the first time, within a time, 1/4 of your time period, 1/4 of the time period of AC, for the first time, AC has maximum value. See, it gets maximum value later also. We are not interested with that. We have to look into the first instance when AC gets the maximum value. That happens in 1/4 of the time period. So basically, you have to find out the time period, and 1/4 of that is your final answer. How will you find time period? That is easy, we know, right? Whenever you're given a function like this is nothing but I is equal to I naught sine omega t. Whenever you're asked to find frequency or time period, you can go for omega value. Omega value will help you to find out this frequency or time interval. So omega is equal to 2 pi by t. We know in this equation, omega is nothing but 200 pi. 200 pi. See, what will be time period then? We can say pi gets cancelled. So t is going to be 1 by 100, right? 200 can be cancelled by 1 and 100. So t is equal to 1 by 100 seconds. But that is not our answer. See, 1 by 100 is one of the options. We need what? 1/4 of that time interval. So be careful. 1/4 of the time interval is going to be the required time is t by 4, which is 1 by 4 into 100, right? So your answer is going to be option B. Got it? Yes. So what is the time at which it hits the maximum value for the first time? That was our question. Yes, and we'll do one more question and then we'll go for a break before the next live sessions. Okay, so let's move on to the last one. Voltage and current in AC circuit are given by V equals to sine 100 pi minus pi by 6 and I is equal to 4 sine 100 pi t plus pi by 6. You are given two functions, right? Instantaneous values of voltage and current. The question is, what is the, the question is given in the options actually. Option says current is leading, voltage is leading, right? So that kind of relations are given, and also phase difference is given. Phase difference. So you have to find out what is the phase difference. That will give you the final answer. So that's an easy question. In the equation itself, we can identify I is omega t plus phi, right? This is minus phi. So which is in lead? Definitely that is current is in lead, right? Current is in lead. If current is in lead, we have two options. Current leads, here also current leads. The only difference, the phase difference are 60 and 30. Okay, so we can find out what exactly is the phase difference. We have the phase of current is 100 pi t minus pi by 6, sorry, plus pi by 6. That is what? That phase of the current, and which is in lead actually, right? And what is the phase of the voltage? 100 pi t minus pi by 6. So the only difference is one is plus pi by 6, the other one is minus pi by 6. Okay, so when you take the phase difference between the phase, this is the phase of the first, phase of the second. You can see 100 pi t gets cancelled. Pi by 6 minus of one more pi by 6, we get the phase difference phi is equal to 2 times pi by 6, which is pi by 3. We need phase difference 60 degree in our final answer. So current is in lead by 60 degree is your correct answer. Current leads the voltage by 60 degree is the option C. Okay, so that is how we find the phase difference and which is in lead. We know how to find it out. Fine, we have more interesting questions from this part. Hopefully we'll do that in some other session, and we'll meet sure in some other sessions with some other questions also from other topics also. Till then, keep going, keep practicing. See, we are in the last lab. Make sure you're not wasting even 1 second. Keep going, and all the best till we meet. Good night.
Hi everyone, welcome to
Amazing channel of Brilliant Katha.
When you're rubbing one body with another body, electrons are transferred from one object to what? Another object. Okay, this process, this type of electricity is been given a name.
halogen connected carbon sp3, then it's connected to benzene. See all of you, halogen connected. What is this carbon hybridization? Full single bond sp3, see then a benzene ring.
Denominator poles shouldn't be included in the denominator poles. That means the denominator, these -1 and -5 should never be included in the solution.
Homocircle caudal fin. It's giving 2 equal lobes. But in case of cartless fishes, look at here, one big lobe is there, one small lobe is there. You cannot cut into 2 equal half this fin.